Sega here, and today we're working on the Go formative. This is the practice test for the Unit 5 assessment. So what I would suggest, if you haven't done this already, go try this first on your own, then we'll go over it together here. You don't need to watch this whole video. Once you do the Go formative, check your answers, and ones that you don't understand, skip forward to this video and watch that explanation here. So first off, we have the swinging stopper in uniform circular motion. Uniform circular motion means that your object is traveling with constant speed, but the velocity is always changing in direction, not magnitude. In fact, you can think of this as the velocity is sometimes traveling left, sometimes traveling down, sometimes traveling right, and sometimes traveling up. So the velocity changes even though the speed stays the same. As the stopper is moving around the circle, we're asked about the velocity, force, and acceleration when it's at this bottom position. Since it's moving clockwise around the circle, that means its velocity points to the left, because tangential velocity is always tangent to the circle. That means perpendicular to the radius. And the centripetal force and centripetal acceleration point towards the center of the circle. That's why I said for number 2, direction 7. Direction 7 was left on the compass. For number 3, I said 1. 1 is the direction of the acceleration because the direction is up towards the center of the circle. Direction 1 on the compass. Same with number 4. The centripetal force is upward, so I put direction 1 up towards the center of the circle. Now the stopper continues to rotate and the string breaks when it's at this position in the top right. Well, that means that its velocity is the only vector that persists. It continues to move forward with this velocity because of its inertia. There's no force pushing it outward because if the string breaks, then the centripetal force has gone away, and so there's no force holding it in circular motion anymore. It goes off along its tangential path because of the inertia of the stopper. So I said that this direction was direction 4, down and to the right. That's why for number 5, I put direction 4. For number 6, inertia is the reason that I chose that direction. It's not getting pushed there. There is no net force after the string breaks. Kepler's third law of motion is the law of harmonics. Has to do with how planets orbit the sun. This is not an orbit, so that's irrelevant. The string can't provide a force on the stopper because once the string breaks, it no longer can apply a force. So now, let's say we have 3 stoppers, and they're spinning around in a circle. We have green, red, and yellow. All of them are having the same period. So they all take the same time to make one cycle because they're attached to each other. If you imagine these as like beads on a string, A can't make a circle faster than B because they're attached to each other. But C has the highest tangential velocity. Because C is on the outside of the circle, its speed is faster than A's or B's. If we use the tangential speed equation, the 2 pi r over t, they all have the same time. That means whichever is at the largest radius must be traveling fastest. Speed is directly proportional to radius. So because C is at the largest radius, it has the largest speed. Now, centripetal acceleration also depends on radius. And if you look at the centripetal acceleration equation, centripetal acceleration is proportional to v squared over r. Because the velocity doubles and the radius doubles for c, c has the largest centripetal acceleration. You can think of this as the same relationship. The acceleration increases with radius. Because think, this would require more force to make that turn. It has to go such a large distance in the same amount of time. It required more force and therefore more acceleration. You could also think of this in terms of proportions. If you had twice the velocity and twice the radius, you also have twice the acceleration, because it'd be 2 squared over 2. Now we've got these circular motion calculations. And here's where it's going to be important for you to picture this scenario.
So I made a demo for you. I'm going to put my safety goggles on. At the end of a string that can move freely through a tube, I have a rubber stopper. That stopper is going to be the mass that is moving. The string can move freely through the tube, and on the bottom I didn't have washers at my house, so it's just a big spool of wire. That provides weight that's equal to the tension along the rope. And if I go at exactly the right speed with the correct radius, the weight of the washers in the center is enough to keep this in equilibrium. The weight of the washers is the centripetal force that allows it to go in uniform circular motion.
Now that we know what that scenario looks like, let's see how to do these calculations. If I'm listing my knowns and unknowns, things I know in this problem, I have the mass of the stopper, and the stopper is the object that's moving. So I'm going to call that M as 125 grams, or 0.125 kilograms. We have a radius of 0.5 meters and a speed of 2 meters per second. But it also gives me the washers. The washers are providing the centripetal force. So the washers' weight is going to be what's providing the centripetal force. So I'm going to keep that in the back of my head here. First, it says calculate the period of the stopper. So this is for number 10. I'm going to write down the equations that have time period in them. I can't use time per cycle. That would be something like, it completes 30 spins in 1 minute. I could use this. I don't have anything like that to calculate the period. But I do have the radius and velocity. Let's use that. I have the velocity is 2. 2 pi r is 0.5. And I'm going to use that to solve for t. 2 times 0.5 is 1, so I have 2 equals 1 over t. Pi stays on the top because that didn't cancel. I'm going to cross multiply t and 2. That leaves t is pi over 2. Or if you want to plug this in your calculator, you get t equals 1.57 seconds. You can also use that. That's why I got t is pi over 2. Calculate the net force on the stopper. I need to use a force equation. And in this case, the net force is the centripetal force. I'm going to use this one. Okay? For number 11, gravity of the washers provides the centripetal force. So I said the centripetal force, the net force, would be the weight of these washers. But since it's the centripetal force, I could also use mv squared over r. In which do I have enough information to solve? I actually have enough to solve the equation on the right, but not the equation on the left. Because this mass, with the dot next to it, is actually the mass of the washers, not the mass of the moving stopper. So let's solve this. Fc is mv squared over r. I would take the mass of the moving stopper times the speed squared, so that's 2 squared, over a radius of 0.5. That gives me a centripetal force of 1 Newton. Then we can use the mass of the washers. So let's say we just used this equation. Right? Well, now that I know that this is 1 Newton, I also know that this is 1 Newton, and I can use it to find the mass of the washers. The washers provide the centripetal force with their weight. So if I take Fg equals mg with a weight of 1 Newton and a gravitational field of 9.8 meters per second, this is a mass of about 1/10, because I'm doing 1 divided by approximately 10. It is 1/10 of a kilogram, or 100 grams. 13, 14, and 15 all have to do with proportions. So let's check out proportions as a method. For number 13, the mass of the washers is increased. That means the centripetal force increases because the washers provide the centripetal force. And the radius of the circle remains the same. What happens to the velocity? I need an equation that relates centripetal force, radius, and velocity. So let's write that out. There's only one equation that relates centripetal force, radius, and velocity. It's asking what happens to velocity if force increases. Force and velocity are related to each other by this square. So that means, since v is in the numerator here, that if force goes up, velocity goes up. And that kind of makes sense to me. I put down for number 13, velocity increases, because if I apply more force, it spins faster. Let's do the same thing for 14. We're going to look at an equation and pick proportions. This says if the radius increases, the mass of the washers, that centripetal force, stays the same. Now what happens to the velocity? So it looks like I'm still taking these 3 variables put together. I'm still looking at the same equation. Okay, here's where it might make sense to do a little rearranging. I want v as a function of r. So I'm going to multiply r to the left. I'm going to divide by m. And then I'm going to take a square root. This is because I want v as a function of r. If I want to one-to-one compare these things, I need to write them in terms of each other. That means radius times centripetal force over mass is equal to velocity. And because of this, I see velocity is directly related to the radius. If radius increases, velocity increases also. So if radius goes up, velocity goes up, and that's why I said what I said for 14. The velocity increases for 14 because as the radius increases, the velocity increases. And you can also think of this in terms of objects traveling in a circle. If the radius is bigger, it has to travel through a larger circle. And since it has to travel through a larger circle, it has to go faster in order to do that. The last problem with proportions, number 15. It says if the mass of the stopper is increased, that's the mass of the moving thing, not the centripetal mass, not like the centripetal force from the washers holding the string together. If the mass increases and the radius and centripetal force remain the same, what happens to the velocity of the stopper? I can use this equation that I already wrote. that relates velocity to the other variables. Velocity is proportional to radius and centripetal force, but is inversely proportional to mass. If I make this a heavier, more massive, more inertia-having object, that makes the velocity smaller. Because I'm applying the same force to a more massive object, it's going to go slower. And that's why I said for 15, velocity decreases. Okay, so let's take a look at part 2. You're working on the International Space Station and you're conducting experiments to measure the force of gravity. You have two objects, M1 and M2. If the magnitude of the gravitational force on M1 is 12 micronewtons, it must also be 12 micronewtons for M2. This is a statement of Newton's third law. If you have M1 and M2, it doesn't matter that they have different masses, they must still experience equal and opposite forces. M1 and M2 experience the same force. So if this one experiences a force of 12, this one also experiences a force of 12. Now it says, if the distance between the masses is doubled, what is the new force of gravity? This is a proportions problem with gravity. Let's take our gravitational attraction equation, that m1 times m2 over r squared is equal to the force. If the distance between the masses is doubled, that makes r twice as big. So I'm going to substitute in this change. R is 2 times as big. Then I'm going to sort. 2 squared is 4. I have 1/4 times the original force. I sorted the new changes to the left in the original equation to the right, and so now I see that the force is 1/4 of the original force. 1/4 of the original 12 micronewtons is 3 micronewtons. So for number 17, I said B, 3 micronewtons, or 1/4 of the force. Okay, so number 18 comes along, and we reset the distance. So I'm back to just having r for the distance. But now, it doubles the mass of m1. Doubling the mass of m1 makes m1 twice as big. So I substituted that change in. All the other variables remain the same though. That means it doubles the force of gravity. It is 2 times this original force. So 2 times the original force is 24 micronewtons, or 2 times bigger. For number 19, notice we're just practicing proportions over and over. We reset the experiment again, but now it doubles m1 and m2, as well as doubles r. So what does that do? Okay, that makes m1 twice as big, m2 is twice as big, and it's 2r in the denominator. But when I sort this out, that's 2 times 2 in the numerator and 2 squared in the denominator. So I get the same force as before. 4 over 4 is 1. So 1 times the original force gives me the original force back. So for number 19, I said 1 times 12 is 12. That is the same force. Part 3, you're a science movie advisor. And you just came back from the International Space Station, so they're like, oh, we'd like to talk to you about your expertise. The movie takes place on this fictional planet named Altair 6, and it has a radius of twice the Earth and a mass of twice the Earth. So let's get this gravitational field expected on Altair 6, and we're going to do this 2 different ways. Way number 1, you're asked for gravitational field. So you can just go take the numbers they give you, right? And take the numbers they give you and solve for the gravitational field. you could say that G is 6.67 times 10 to the negative 11, M is 12 times 10 to the 24 kilograms, and that the radius is 12 times 10 to the 6th meters, and we square it in the denominator. Method number 1 to solve this problem is just solve it. Take your value for G, take the mass of this planet, divide by r squared. Notice when I put this into my calculator, I'm going to make sure I put in parentheses. If you don't put in parentheses, it doesn't work. This gives a gravitational field of 5.56 newtons per kilogram. So method 1, if you're good at math and you just want to do this out, substitute in your numbers, get an actual answer. Alternatively, what you could do is you could do this proportionally. We want to compare this to the gravitational field of the Earth. It has double the mass and twice the radius. If I sort the 2's to the front, I have 2 in the numerator, 4 in the denominator. That leaves 1/2 of the original gravitational field of the Earth. 1/2 of the original gravitational field of the Earth. So 1/2 of 9.8 is approximately 5. And so that's why in either method, I'm getting B, about half that of Earth. Now, once you get that value, right? Now I've got this person astronaut. Now I've got this person astronaut, and they are on the planet's surface, and we want to figure out how much they weigh. Well, remember, when you're on a planet's surface, you can just use Fg as mg. So I could take my 100 kilogram astronaut times 5 as the gravitational field, and that gives me about 500 for their weight. I don't need to do the larger gravitational force equation, but you actually could if you wanted to. If you want to do the universal gravity with G is 6.67, M is the mass of this planet, so 12 times 10 to the 24, M is the mass of the astronaut, is 100, and R is 12 times 10 to the negative 6th, you totally can. You will literally get the same answer. Okay. So now we take our astronaut, and I have to use the universal gravity equation. I know I have to use the universal gravity equation because in number 22, the astronaut's too far from the surface of the planet. In number 22, I have to use universal gravity because the astronaut's floating over here. So I would use the universal gravity equation. And this one you are going to need to put into your calculator. Substitute in your 6.67 times 10 to the negative 11. That will always be your value for G. M1 is the mass of the planet. So that's 12 times 10 to the 24. M2 is your astronaut. That's 100. The radius is your 20 times 10 to the 6th. And that whole quantity is squared in the denominator. This gets me a force of 200 newtons. And let's see if this makes sense. On the surface of the planet, they weighed 500 newtons. When they're far from the center of the planet, they weigh less. That makes sense to me. Number 23. They want to know how different variables affect the orbital speed. Since orbital speed is what they're asking about, let's look at the orbital speed equation. The speed depends on the universe we're in, that's G, the 6.67 times 10 to the negative 11, the mass of the central object, which is the planet. It's a satellite going around the planet, so that doesn't depend on the mass of the satellite, and R, the distance from the planet. So let's see what increases the orbital speed. The mass of the planet increases the orbital speed because as big M increases, V increases. m and v are proportional to each other. Having a larger planet means that you would go faster in orbit around it because it has a larger gravitational field. The mass of the satellite doesn't matter. See how there's no little m in here? So the mass of the satellite has no effect. No effect. Finally, the radial distance. The radius is in the denominator. That means if the radius is larger, the velocity is smaller because one's in the denominator and one's in the numerator. Having a larger radius means there's less gravitational force at that location, so it will go slower. For number 24, 3 cast members are arguing about what speed a second satellite would need to be if it had twice the orbital radius. So let's picture this in our heads. We have our planet, satellite number 1 with its radius, and satellite number 2, which has twice the radius. How would the orbital speed compare? If the radius doubled, the orbital speed would have to decrease. And let us check how it would decrease. If I put a 2 for twice the radius here, and then separate these out like I was doing with proportions before, I end up with a square root of 2 in the denominator and 1 in the numerator. So I see that this number decreases the speed. The speed would be traveling more slowly, so Chris must be right. Chris says the second satellite would need to be traveling more slowly since velocity of the satellite squared is inversely proportional to the radius. Actually, what Chris is saying is square both sides of this. Velocity squared is inversely proportional to the radius, so imagine I take a square of both sides. That makes this v squared. That makes this v gm over r. He's saying velocity squared is proportional to the inverse of the radius, so if I double the radius, the velocity decreases. We're both saying the same thing. For 25, parts of the movie involves using a radar mapping system to map the other planets in Altair's solar system. The satellite needs to maintain a specific distance from the planet, so the radius remains the same. If the satellite is to maintain the same orbit with the same radius but have a larger mass, I would need a higher velocity for a larger mass planet. That's actually asking about this again. If the mass of the planet goes up, the speed of my satellite would increase. So for number 25, I said C. It needs to go faster in order to stably orbit a larger planet. Finally, on to Kepler's laws. For Kepler's laws, 26, which point has the greatest gravitational potential energy? That would be point D. Because it's farthest from the sun, it has more gravitational potential energy. At point D, if you imagine that this distance is the height from the sun, D has the largest height, so it would have the largest PEG. But point A would have the largest velocity. Because the closer you are to the sun, the more gravitational force, the faster you go. All of the points would have the same mechanical energy though. Because think of it like this. At A, you'd have lots of kinetic energy and just a little tiny bit of potential because you're close to the sun, so your potential is small. That would give you the same energy at D. At D, you'd have a small kinetic energy where you're going slowly and a larger gravitational potential energy because you're far from the sun. 29, I'm imagining the area like in Kepler's second law. If these each represent 24 hours in the orbit, then these have to have equal areas to each other. Areas 1 and 2 would be equal to each other by Kepler's second law, the law of equal areas in equal times. Okay, almost done. Last three problems are dealing with proportions, dealing with Kepler's law of harmonics, also called the law of periods. This is the law that says that the radius cubed is proportional to t squared. That as long as your objects are all orbiting the same thing, in this case they're all orbiting the central mass of the star around Altair, that all of these must have a direct relationship. Now, it says use the graph to calculate the period of Altair's orbit in years. So let's take this data point. It says that it has 4 is equal to period squared. So for number 30, if 4 is equal to period squared for the planet Altair, that must mean the time is equal to 2 years. All right, what about for the radius of orbit of Altair? I'm going to pull this line over to the left and read the value off the chart. It looks like this radius is about 125, but that's not really radius. It's radius cubed is equal to 125. So for 31, radius cubed is equal to 125. If you haven't seen what a cube root looks like in your calculator before, it looks something like this. I use this button up here, the power button, to raise it to the 1/3 power, and I use the parentheses to make sure it doesn't think I'm doing 125 to the first power and dividing it by 3. That's where I got the 5 from. It's 5 because when I do the cube root of 125, the radius is going to be 5, and the units are billions of kilometers. Since it's billions of kilometers on this axis, I don't need to convert farther from there. It's already in the correct unit. The last one. I'm going to show you a few different methods for 32. First, let's do the graphical method. During the story, a main character discovers a new planet with an orbital period of 3 years. Calculate the radius of the new planet's orbit. From the graph, I know that I need to plot t squared versus r cubed. In this case, if the planet's orbit is 3 years, then I would be plotting at 9. T squared would equal 9. So when I plot the point 9, I can read r cubed off this chart. And I see that it's between, let's check. It looks like it's between 200. Let's go up to 9 and over. Between 250 and 300. Let's call that r cubed is about 275. If I read the graph and see that r cubed is about 275, that must mean r is 275 to the 1/3 power. R is about 6.5, and whatever units are on the y-axis. Billions of kilometers were on the y-axis, so 6.5 billion kilometers for the radius. Another method you could use is you could use a chart, like we did in experiment 5C. If I take the planet Altair and the new planet, I can compare them side by side. I can take their time, radius, time squared, r cubed, and the quotient, t squared divided by r cubed, should be a constant. The planet Altair had a time of 2, a radius of 5, and that leaves t squared as 4 and r cubed is 125. Dividing these out gets 0.032. But this value is a constant that has to be true for everything that orbits the same central mass. That means my new planet must also have this constant. So if its time period is 3, that means t squared is 9, I can solve for r cubed. I know that t squared divided by r cubed must be equal to 0.32 for this new planet as well. Since t squared is 9, I can solve for r cubed precisely. I'd multiply r cubed to the right and divide 0.32 to the left, or 0.032 to the left. This quotient gives 281 is equal to r cubed. Let's try this out. 281 to the 1/3 power is 6.5. R is 6.54. In the same units, billions of kilometers. That's two different ways to do the same problem, and it works on the same principle. That in a solar system where they're all orbiting the same thing, points must all fall along this line, and they must all have the same universal gravity constant between the two of them. All right, guys, that is it for the review. Good luck.